So I'm going to do the introductory portion, which is just some basic info about what Bayesian inference is, the main ideas that underlie it, and the materials for this workshop are all on the OSF, and there's an OSF link right at the bottom of our slides there, osf.io/9NWEP. And oh, I just got a poll. I'll close that. So I'll just get started here. So with Bayesian statistics, there are just a couple of ideas that underlie everything that you do. In my opinion, it's very magical, and you'll see why through the examples. So in Bayesian statistics, we have uncertainty about the world. That might be a scientific claim or a hypothesis. And we use data to update what we know and to reduce our uncertainty. And what the data do is they update our prior uncertainty to posterior uncertainty, is what we call them. And these uncertainties are represented with probabilities. So any inferences that we make about a scientific claim or a hypothesis, these are in probability statements about their truth values. So the first example I want to go through is called The Happy Herbologist. And this is a story about Professor Sprout, who leads the herbology department at Hogwarts. And she's developing a spell to evaluate the quality of a magical plant called the green caudicle. Now, this is a leaf that when consumed, it causes a witch or a wizard to feel euphoric and relaxed. It's the same sort of leaf that Canada legalized recently, and California before that. So it's very popular at Hogwarts, it turns out. Now, there's a problem here with the green caudicle where a mutation affecting 1 in 100 caudicle plants will change its effect, and those rare plants will cause unpleasant side effects, which include paranoia and anxiety. It also, just leads to a bad time. So what Sprout has done, being a good herbologist, is that she's developed a spell that has a 95% chance to detect any mutation that's present. But it also has a 2% chance to falsely indicate that a healthy plant is actually a mutant. So in statistical terms, we might say that the 2% chance would be the false positive chance, and the 95% chance would be the true positive chance. So what we want to know is, what is the probability that a given caudicle plant really is a mutant when Sprout's spell says that it is? Because then if you are confident that it's not a mutant, then you could consume it. So Bayesian inference is really about leveraging all the information we have and all of our knowledge to make the optimal inference. So for this problem, we should ask, what information do we have? Well, we know that the 1 out of 100 caudicle plants are a mutant strain. So our probability before having any data is that there's a 1% chance that any given plant is a mutant. And that means that there's a 99% chance that any given plant that we'd pick at random is healthy. And we also know that Professor Sprout's spell isn't a perfect spell. So there's a 95% chance that the spell says, yes, that's a mutant, when the plant is actually a mutant. But there's also a 2% chance that it says, yes, that's a mutant, when actually it's a healthy plant. So the little plus sign just means the spell says that the plant is a mutant. So to visualize what Bayes' theorem is going to do, I have a little diagram, and what we imagine is that we take 100,000 plants and we say, okay, well, before I cast the spell, I know that 1% of these plants will be a mutant plant. So what we can do is we can draw a little arrow to the mutant box, and we know that 1% of 100,000 is 1,000. So we know that ahead of time, 1,000 of these plants will be mutant plants. Then we can ask, well, if the spell is now cast on one of these mutant plants, well, 95% chance of saying that, yes, this is a mutant means 5% chance that it will miss it and it won't say it's a mutant. So we can just call these positive and negative, and 95% of these 1,000 will go to the positive box and it will say, yep, that's a mutant right there. But 50 of them will get categorized as healthy. But now the other 99% of plants are actually healthy plants. So we have an arrow pointing to healthy and the number 99,000, meaning that 99,000 of the 100,000 plants are actually healthy plants. And we know that of the healthy plants, when Sprout casts a spell, then there's a 2% chance that it comes back positive, saying that's a mutant plant, which would be wrong. And there's a 98% chance that it comes back negative, which would be correct. So we draw the same two boxes and we take 2% of the 99,000 and those go to the positive box. And we take 98% of the 99,000 and that goes to the negative box. So what we've done now is we've sort of looked forward thinking. So we say, you know, we take all these plants, they're either a mutant or they're healthy. If they're a mutant, this many go to the positive. If they're healthy, this many go to the positive. Well, that's not really what our question was about. Our question was about what's the probability that a plant is a mutant after we return a positive result. So we really only care about the state of the world where we get a positive result. So what we're going to do is actually turn the picture around. So we're going to collect all the positive results and we're going to see how those ones get distributed. So we had 950 mutant plants that gave us a positive result, and we had 1,980 healthy plants that gave us a positive result. So for a total of 2,930 positive plants or positive results. So all we're going to do is look at the proportion of these almost 3,000 plants that actually came from the mutant box. So we just take 950 out of 2,930. So when we do that, we get the proportion of the plants that got a positive diagnosis, but that were actually a mutant. And that number is 950 out of 950 plus 1980, which will give us 0.324. So about a third of about a probability of 1/3. So if we get a positive diagnosis from Sprout's spell, there's actually only a 1/3 chance that the plant is actually a mutant plant. So it's still better off, you could, you know, risk it and consume it, and there's a 66% chance that you'd be okay, rather than that 33% chance where you would experience the bad side effects. But what I want to highlight here is that we just used Bayes' theorem, and it wasn't that complicated, right? All we did was look at, well, we have this many plants, which box do they go to, collect the boxes that we think are relevant, and then turn them around. Now, when you see Bayes' theorem presented in textbooks and in papers, it's always presented with this big, long formula, right? You have the So if M just means the plant is a mutant and H maybe means that it's healthy, we'll just use those to shorten everything here. Well, we can write the posterior probability, so the probability of M given a positive spell diagnosis, and it's a function of all these complicated probabilities, but in the end, it just results in us drawing the picture and looking at the proportion of findings that were in one box versus another box. So I really like this example because it just puts Bayes' theorem sort of into a simple scenario and shows you that the formula itself, while it looks pretty complicated, is actually just drawing some arrows between boxes and comparing a couple of numbers. So what I'd like to do next is talk about something more sort of philosophical, more broad, which is the Bayesian inductive cycle, we call it. And here's a picture of Thomas Bayes, allegedly. It's actually unclear whether the common picture you see of him is really him. But if we take this guy as Thomas Bayes, then he's in the center of this cycle. So what we have at the top is our prior knowledge, and that represents what we know about the world or our hypothesis before we've done any data collection for whatever we're going to do. And from our prior knowledge, we can make a prediction about what we would see if we ran an experiment or we collected some data. And then once we've made a prediction, we can go and actually collect the data. And we can see how our prediction was right or wrong in what it said about what we would see compared to what we actually saw. And what we can do is take this prediction error and use it to update our knowledge. And when we update our knowledge, we can take that forward to the next problem and use that as our new prior knowledge. So we can do this in a cycle and iteratively update what we know. And the next example I'm going to show you is illustrating just that. So Bayesian inference obviously relies on Bayes' theorem. I mean, that's in the name. And when we write it out in that complicated form we saw earlier, we can actually collapse the denominator just into something simple. So this is the same formula, it's just written a little differently. So we have our posterior probability. So in this case, we're using theta, the symbol, for meaning our unknown quantity or state of the world. It's sort of generic. And y just means the data. So we have something theta given y, that's probability of theta given that we observe y, and that's equal to the prior probability of theta times what will happen for y given the state of theta, that's called the likelihood, and then we divide that by what's called the marginal probability, and that's just we'll see that in a minute. That's sort of complicated. And usually Bayes' theorem is written like this, but it's actually, I think, a little bit better to write it a different way. And that's what this example will illustrate. So what we can do is we can think of Bayes' theorem in terms of predictive updating. So what we do is we take those last two terms and we group them together into a single term. So we take the posterior probability of theta given y is equal to the prior probability, but it's changed by some updating factor. So to get to the new probability, we have to either multiply this number by something bigger than 1, so it gets bigger, you have a higher probability after seeing the data, or you multiply it by something smaller than 1, so that it gets less likely after seeing the data. And that's what this updating factor is doing. So for this example, I want to show you where does that updating factor come from and what does it actually mean. So this example is called the perfection of the puking pastille, another Harry Potter example. So in the secretive research and development laboratory of Weasley's Wizarding Wheezies, George Weasley works to develop gag toys and prank foods for the entertainment of young witches and wizards. Now, if you've followed the story, you know why it's only George, but I don't want to do it too much spoilers. Well, in a recent project, Weasley is studying the effect of his store's infamous puking pastilles, which are designed to cause immediate vomiting when consumed. You actually vomit these very rainbow colors, so that's why I've got that picture there. And the target audience for the Wheezies is Hogwarts students who need an excuse to leave class and enjoy making a terrible mess. Now, shortly after the new version of the pastilles hit the store shelves, customers began to report that puking pastilles do not always cause what we'll call expulsion events, in case anybody's eating their breakfast right now. Now, to learn more about this unknown behavior, George turns to his sister Ginny, who it turns out is an accomplished statistician, and together they decide to set up an exploratory study. Now, since the outcome of interest is a series of binary yes-no trials, Ginny recommends modeling the number of expulsion events with a binomial distribution. That's pretty standard. But before collecting further data, since we're doing a Bayesian analysis, the Weasleys have to specify what they believe to be reasonable values for the expulsion probability based on the reports that George has received. So before they collect any new data, what do they think is the chance that you take a Wheezy or, a pastille, I've been calling it a Wheezy, a pastille, and then you have an expulsion event. So since theta is any value between 0 and 1, right, we don't know, but it can't be bigger than 1 because it's a probability, it can't be smaller than 0. Ginny decides to model George's partial knowledge with a beta distribution. And that's just a standard distribution that's in any probability textbook. Now, I pulled this picture from Wikipedia, but it's just to illustrate what a beta distribution even is. So a beta distribution has two inputs, and they usually get called A and B. So the first one, A, can be between 0 and infinity, and the same for B. And if A is bigger than B, then you get a distribution that sort of favors values bigger than 1/2. And if A and B are equal, then it will be symmetrical around 1/2. And if, I don't have an example here, but if B is bigger than A, then it's favors values below 1/2. So in this case, if in the blue case, if A and B are equal to 10, then it's symmetrical around 1/2 and sort of narrow. And as the numbers get bigger and bigger, that distribution will get narrower and narrower. And as the numbers get smaller and smaller, it will get wider. And eventually, if they get smaller than 1, then you get this bowl shape, which is kind of funky. So George and Ginny use a prior elicitation package that exists out there, and they come up with this funky beta distribution, which has values of A of 2.33 and a value of B of 1.88. And so what we have is we have this distribution if I plot it out. So it's very broad, right? They don't have very many preliminary reports. They don't know much about this probability that you will bleh after you take a pastille. So it's super broad, but it's mostly, you know, between 0.4 and 0.8, but there's a chance that it's below 0.2 and even a chance that it's above 0.8. So this is our prior distribution for theta. Now, the next step of the inductive cycle is to generate a prediction for what we'll see in the experiment. So what is the experiment going to be? It turns out they're going to collect 20 volunteers and give them 1 puking pastille each. So we're going to have a sample size of 20 in this experiment. Now, based on our inductive cycle, we need to generate a prediction about what the data will look like when we run the experiment. And that is that marginal term that we saw earlier, that probability of y, or the probability of the data. So when we do that, we get something that looks like this. So on the x-axis, it's just the number of expulsion events that will occur in the 20 trials. And each bar's height represents the probability that we will see that many expulsion events. So for example, there's less than 1% chance we see 0 based on this prior distribution. There's a little over 1% chance that we see 1, and so on, up to about 7% chance that we see 12. And you can see that this shape really looks a lot like that prior distribution. And that's because what we're doing is we are making an average prediction. So if we had a single value of theta, like 1/2, we would know that the highest probability would be around 10 or 11 or 12. And if we had a probability of, say, 0.8 or 0.9, the most likely outcomes would be around 18 or 19 out of 20. But we don't know what the value is. It could have been any of those values. And some of them are more likely than not. So what we do is we upweight the predictions made by the ones that are most likely. And that's why the prior predictive distribution is what this is called, or the marginal distribution, really looks a lot like the prior. So it turns out in the experiment, when they go collect the data, they get 15 out of 20 trials result in an expulsion event. So that's a proportion of 75%. So what do we do with this? Well, we have our data. The next step in the induction cycle is to calculate our prediction error. So we want to know how correct or incorrect we were in our prediction. So that's what we're going to do next. So with a binomial data model for 15 out of 20 trials being successful meaning having an expulsion event, and with our prior distribution, P of theta, modeled as this beta distribution that we saw, then the probability of getting 15 out of 20 was 0.065. And I just pulled that right from that picture. And now we can compare the probability that each value of theta gave to 15 out of 20 and compare that to the average probability. So the reason this is called the marginal probability is because it's an average. So we want to compare how well each value of theta does to the average. And the ones that do well will get a boost, and the ones that do poorly will downweight them. So how do we do that? Well, what we're going to do is just compute the probability of getting 15 out of 20 successes, 15 successes in 20 trials, for every value that theta could possibly take. So to look at this graph, I have the value of theta on the x-axis, which ranges from 0 to 1. And on the y-axis is the probability that that value of theta assigns to 15 out of 20. So just to look at a couple of values, let's look at 1/2. So if it really was a 50-50 chance that you eat a pastille and then you have an expulsion event, then there's actually a very small probability that you would see 15 out of 20. And if it's 0.4 or 0.2 is the real chance that you have an expulsion event, then it's even less likely that you'll get 15 out of 20. Now, conversely, if it's really a 60% chance that you consume a pastille and have an expulsion event, then there's about 0.075% chance of getting 15 out of 20. And that number rises and rises. And if the true value of the success chance is 0.75, then this peaks and we have about a 20% chance of getting 15 out of 20 successes, 15 successes in 20 trials. And then it drops again because as the chance gets bigger and bigger, you're less likely to get so few as 15 out of 20. So this plot just collects all those probabilities, so from 0 to 1. And what we want to do is compare this probability. So say we're looking at 0.6, right? Well, if we compare this probability, which is 0.075, we want to compare that to our average probability and see if it's bigger or smaller. So what I'm going to do is just draw a horizontal line on this figure. And that line represents that average probability we saw earlier, that prediction that it made for 15 out of 20. So what we see is that some of these values gave a higher probability than the average, which is the red line, and some of them gave a lower probability than the average. So what happens is that the values of theta, which is the success chance or the expulsion probability, the values of theta that have their point above the red line will have their posterior probabilities higher than their prior probabilities. So their probability will go up because they did a good job predicting the data compared to the average. And conversely, values of theta that fall below the line will have their probabilities decreased, and they will become less plausible because they do a poor job predicting the data. So if we just look at this plot, what would we can do a mini induction cycle ourselves and make a prediction about what the posterior will look like relative to the prior. So based on what I've told you, the values where the dotted line is above the red line should have the posterior density go up, and the ones below the red line should have it go down. So around 0.6 or so and around 0.9 or so, we should see the posterior higher, and outside that window, it should be lower. And that's exactly what we see when we plot the posterior now versus the prior. So the posterior is the thicker line here, and it's the more peaked one. And we see that at about 0.6, we see an increase. The posterior will be higher than the prior for values above 0.6 and smaller than 0.9. And then the values outside that window, they become pretty unlikely by around 0.4 or by around 0.95. So what we've done with this example is just complete the inductive cycle by stating our prior knowledge before collecting any data, making a prediction about what we will see in our experiment, and then we collect the data and we check our prediction error, which was with the red line, and then we update what we know. And the posterior represents what we know now about the expulsion probability after we've ran our little experiment. So what Bayes' theorem does is it combines information in what I think is an intuitive way. So values of theta become more or less plausible according to how well they predict the data that are observed. And in this case, the posterior distribution has a known form. It's really nice. It's not always like that, where you end up with this beta distribution again, but with new parameters of 17.33 and 6.88. And that's what I plotted before. And yes.
So I just had a very nice question.
Okay.
On the Q&A thing.
What's that?
So it says it's by Keith, and he's saying, I'm curious about Ginny's choice of a beta distribution. What other options did she have? How did she decide among them? And what are the implications of choosing another option? So
Ah,
maybe it's nice to tell a little bit more about how to choose a prior distribution and yeah, what
sure.
other options she had, maybe.
Sure. So the beta distribution is nice for this case because it respects what we know about the parameter. So if we know that the value has to lie between 0 and 1, a beta distribution does that. So you could have used something else, certainly. You could have taken a normal distribution and truncated it and said, well, we'll just say, if it's below 0, we don't count it. And if it's above 1, we don't count it. And that's fine too. You can do that in a lot of software. But in general, you want to stick with distributions that naturally follow your boundaries. So a beta distribution is useful for that. I don't know too many distributions that um, only span 0 to 1, and that's probably why the beta is so popular for this sort of thing. But if you don't have a bound, right, if it could go minus infinity to infinity, then you could just use anything else that follows that bound. So a normal distribution is really common for that, but you could also use a t distribution or a Cauchy distribution, and we'll see a couple of those later. Now, in terms of the beta distribution and choosing the parameters for it, right? So I sort of glossed over that point for the sake of time, but there are some tools out there that give you a little Q&A, and it'll say, what do you think is the chance that theta is bigger than this number and less than this number, or what's your expected value? And then it sort of back computes the numbers for the beta distribution. And then you can plot it and look at it and say whether or not you think that it represents what you really think about that parameter. And those are really nice. And I'll link to one of those in the chat when I get a minute here. And so those are nice tools. But what's really the most important thing is that if you're choosing between a couple of priors, you can go and do a sensitivity check. And if they all come to roughly the same conclusion, then you're safe and you don't really need to worry about it too much. And if they come to really different conclusions, then you would want to acknowledge that and say, people with different starting opinions about this, or different background information maybe, they might come to different conclusions. And I think that's natural, right? I mean, that's what happens when we read an article and the authors argue for X and you go, well, I don't really buy that. Or maybe you're arguing for it and your reviewers don't buy it, for example. But I think there's room for scientific disagreement. And what's nice about the priors is that they really formalize it. So they make it transparent where that disagreement might come from. So just to wrap this up, this posterior distribution that George and Ginny have derived in this example, it allows them to point at the most plausible values for the probability of an expulsion event occurring, right? Those are the values with high density. You can find the probability that the expulsion rate is larger or smaller than any given number. So if I look at my picture here, I can just say I want to know the probability that the expulsion rate is higher than 0.8. All I need to do is find out how much of this distribution lies beyond 0.8. And there are nice calls in R that will do that for you, called the quantile functions. And what you can also do is find an interval that contains the expulsion probability with a certain probability. Well, it gets confusing when we have probabilities of probabilities, but I guess I wrote expulsion chance to try to be a little bit less confusing with that. And that's what's called a credible interval. So going back to our posterior, we might say there's a 95% chance that the expulsion probability is between I don't know, I can't read it off of this, but maybe 0.55 to 0.85, something like that. And you can compute that and directly state the probability that this parameter is between this number and this number, which is really nice, and which some people think that you get out of a confidence interval, but it turns out you can't actually do that. And that's the only thing I'll knock on the classic ways of doing this stuff. And I think with that, I'm going to transition to giving Julia the monitor here, and we're going to switch seats. So you're going to see her sit down, and let me just stop sharing the screen and switch it.
Stop sharing.
So first of all, I want to point out again that we have an OSF repository. It's here, and it's also on all of the slides. So if you want to look at that, all the slides, Alex's slides and my slides are on there. And there are also data sets and some applications and some things you can try out with JASP and Bayesian statistics. Okay, so let me start here. So first of all, we gave you a poll question in the beginning, what your experience with Bayesian statistics is, and it seems that at least everybody has heard of it, and some people have actually used it, and I hope that by the end of this webinar, you'll be able to use a little bit more. And one aspect that we want to show you is the Bayesian t-test and how to perform one in JASP. Okay. Sorry, guys. This is funny. Okay. It's not doing anything.
You can use the arrow keys.
No, I can't. That's fine. Okay, so what Alex has showed you so far is how to consider one model in Bayesian statistics. And what I'm going to talk about is Bayesian hypothesis testing, which means that you need at least 2 models. That means that you have to do something that is very similar to the Bayesian inductive cycle that Alex showed you. So first we are starting out with some theoretical constraint, and we specify models, a target model and some alternatives models. From these theoretical constraints, we analyze these models and compare them and use them for statistical inference. And from the statistical inference, we get an interpretation, and we can get inference about theory. And so in the t-test, we only compare 2 models to each other, and that's what I'm going to talk about today. The target constraint is the null hypothesis, and then there's an alternative constraint, like there is an effect, or we compare these 2 models. So suppose we have these 2 models. H0 will be the null hypothesis, and H1 will be the alternative hypothesis. Then our question in Bayesian statistics is which model is better supported by the data? And the answer is the model that predicted the data best before we ever looked at the data or we collected the data. And so the ratio of these predictive performances between the 2 models, that is known as the Bayes factor. And the Bayes factor is what we will use for Bayesian hypothesis testing and model comparison. And Alex already showed you that Bayes factor in a way, or one aspect of it. So to do that, we again need Bayes' theorem. We start out with prior beliefs about our hypotheses. So there's a probability of the alternative hypothesis and the probability of the null hypothesis, and the ratio of these is this term here. And we update the term given our data. So what's the probability of the data given the alternative hypothesis divided by the probability of the data given the null hypothesis? This is the predictive updating factor. And as a result of this multiplication, we'll get the posterior beliefs about the hypotheses. So the probability of the alternative given the data divided by the probability of the null hypothesis given the data. And these terms are often coined as the prior odds, and we multiply those by the Bayes factor to get the posterior odds. And the Bayes factor here has the alternative hypothesis in the numerator, and that means that the it's the Bayes factor of the alternative over the null hypothesis. So just to illustrate all these terms, we have prior odds here. That means it's the probability before we see the data of the alternative hypothesis over the null. The probability of the null, if you only have two models, is just 1 minus the probability of the alternative. And people can start out with different prior odds. So say we're looking at some hypothesis in psychology, like there is a subliminal priming or something like that. Then some person could say, well, the probability that there is subliminal priming is 0.4. And someone else could say, well, maybe I think it's definitely like there's a good probability here that the alternative is true. So my probability is 0.75. We can have different starting points before seeing the data. And then after seeing the data, everybody moves. Say we observed a null effect. Everybody moves closer towards the null. But we can also have different endpoints. And so this is the posterior odds illustrated. Everybody can end up at a different point on this probability line at different updated locations. But the step we take is going to be the same. And that's quantified by the Bayes factor. And this is why people think it's interesting to look at the Bayes factor in papers, for example, and to report them, because the Bayes factor is going to be the same for everyone. What your prior beliefs are, that's up to you as a reader and as a researcher. What you end up with as a belief after seeing the data, that's also to a degree up to you, but the updating factor is going to be constant across all of us. Just to give you some examples of interpretations of the Bayes factor. So if we have a Bayes factor in favor of the alternative over the null of 10, that means that the data are 10 times more likely under the alternative than under the null hypothesis. If the Bayes factor is 1 over 10, we could flip it to say the Bayes factor for the null hypothesis over the alternative is 10. So these here are equivalent statements. And that means that the data are 10 times more likely under the null hypothesis than under the alternative hypothesis. And then there could also be a case where the Bayes factor is 1. And that means that the data are equally likely under the two hypotheses. So just to give you a little bit more of an interpretation, we could use this little comic strip here. And so what we want to interpret the Bayes factor as is the strength of evidence between the two hypotheses. So here's the Bayes factor again, probability of the data given the alternative over the probability of the data given the null. And say we have a Bayes factor of 3, that means a Bayes factor of 3 to 1. We have 3 balloons for the alternative and 1 balloon for the null. We could create a pizza plot out of this. So we have 3/4 of that pizza blue and 1/4 is yellow. And if we would put an arrow on there or something and spin it, the question is, where does the arrow land in this case? And so, you know, we could spin it a few times, and the level of imagined surprise of where, whether the arrow lands on a blue or on a yellow area, that's something like an intuition for the strength of evidence that the Bayes factor provides. So imagine we had 10 balloons to 1 balloon, 10 blue and 1 yellow. That would mean the yellow balloon, it would be pretty unlikely that that arrow ends up on the yellow balloon. If we had 100 blue balloons and 1 yellow balloon, that makes it even more unlikely, and I would be really surprised if the arrow ends up there. For 3 to 1, it's probably not that surprising, so it's just less evidence. A lot of people ask, well, yeah, that's all nice and stuff, but I want to know what a big Bayes factor is. Don't we have cutoffs like we do in frequentist statistics? Where's my alpha level? How can I, you know, quantify a lot of evidence? And well, that's really context dependent would be my answer. How many balloons really are a lot of balloons? If you have a kid's birthday party with 20 kids, then 3 balloons is not a lot. But if it's just the one kid with its birthday in the morning with just the family, then 3 balloons is a decent amount of balloons. And so it really just depends on the context you're in. to translate that to research, there are also different questions that where you really want to have a lot of evidence, and in other situations you may be okay with less evidence. And if you are one of the many people who really want to have cutoff values, there are a lot of papers that provide tables to use in some argument, and you can take a look at those. I won't give them to you. All right, so let's focus in on Bayesian t-tests. So far, we just looked at Bayesian model comparison. And let me give you a data example. And this one is originally developed from Topolinski and Sparenberg in 2012. They had an experiment where the idea was that moving your hands clockwise increases openness to a novelty. As well, clockwise motion means on a watch, right, a future orientation, and that should increase openness. While if you move your hand counterclockwise, that means a past orientation, and that means we would expect less openness. And so there was also a replication attempt of this by Warenmakers et al. And they had a study with 100 participants who completed a personality inventory. And during the completion of that inventory, participants rotated paper towels on these little operators over here. And so the theoretical prediction was that the direction of the rotation would predict openness scores in that personality inventory. To analyze this statistically, we need models. And this is something that's not only true in Bayesian statistics, this is also true in frequentist statistics. So let's take a look at the t-test models that typically are used in any type of statistics. For that, we need a distribution of the data. And so we have two conditions here, the clockwise condition and the counterclockwise condition. Both of them have the data distributed as normal distributions with common variance terms, sigma squared. And the most general model would say, well, the means do not have to be equal. And the research question of interest is whether the means are equal or not. Is mu x equal to mu y? We could also put that in terms of the population effect size delta. The population effect size is a standardized difference of the means, standardized on the population standard deviation sigma. And so if we do that, we could translate the question whether mu x is mu y into is delta equal to 0. So this is just the question that everybody's interested in. Is the effect size 0 or is it not? The null hypothesis would state exactly that. Delta is 0, which means we could simplify the model on the data so that both x, the clockwise condition, and y, the counterclockwise condition data, come from normal distributions with the same common mean mu and the same common variance term sigma squared. And to translate into psychology, that means that there is no effect of rotation direction on openness scores. The alternative model says something different. It says that there is an effect of rotation direction. And so to analyze that, let's define an effect here, beta. That's just the difference between mu x and mu y, the means of the two distributions. And so if we do that, we can rewrite the distributions of y and x this way. Let me just go forward. And that also means that the population, standardized population effect size is beta divided by sigma. And the alternative hypothesis states that this term here is different from 0. This is just the same in frequentist and Bayesian so far. So let's take a look at the data and first analyze it frequentist, and then we take a look at how to analyze it Bayesian. So here is the data. The mean openness score in the clockwise condition is 0.64 and the counterclockwise condition 0.71. And remember the theoretical prediction was that the clockwise condition should have a higher score of openness than the counterclockwise condition. Which means that we have a t-test here. If we do a frequentist t-test, we get a p-value of 0.453 and an observed sample effect size of negative 0.149. So it's the effect is in the opposite direction than expected. And the problem here in frequentist world is that we can only we fail to reject the null hypothesis, but we can't accept it. So we have absence of evidence for an effect, but we don't have evidence for the absence of an effect. And that's where Bayesian analysis comes in and where it's really useful. And to do a Bayesian analysis of this data, we need priors for our distributions, for our different parameters here. So we have the mean parameter mu, we have a variance sigma squared, and then we can place a prior on the standardized population effect size delta. Mu and sigma squared, if you remember back to the models, is common across the null and the alternative, which means the prior we put on these two parameters is not going to affect the Bayes factor substantially. And so we can just place reference priors, as we call them, on mu and sigma squared. The advantage of that is that these priors are scale invariant. So that means that it doesn't really matter in which units you assess your data. Say you have response time data. It doesn't matter if you have them in milliseconds, seconds, or hours. That's not going to affect any of the aspects of these parameters or the priors. And you can place the same prior on all of these different types of data. So this is the term for this prior distribution. The really interesting or important prior setting is on delta, the population effect size. And it's been often recommended, and this is what we use in JASP as well, to, as a default, to put Cauchy priors on the effect size. This is what that would look like. The effect size comes from a Cauchy distribution with some scale setting R. Let me show you a plot of a Cauchy distribution in case you don't know what that looks like. So the gray line here as a reference is a standard normal distribution. And that means it's zero-centered and it's spread around. A lot of the mass of this distribution is between -2 and 2. And the Cauchy distribution with a scale of 1, say, is this blue dotted line here. And then the default setting in a lot of statistical packages and in JASP as well is the Cauchy with a scale of 0.707 or square root of 2/2. That's the same thing. That's the red line here. And as you can see, it's a little bit more, there's a little bit more mass on smaller values, but there's also a little bit more mass out here. So it's not quite as restricting as, say, a standard normal. If there's a value that is very large, this Cauchy distribution will still capture it. And I also have these small lines in here that just show the area of expected effect sizes in psychology. So this is between -0.8 and 0.8. That's where a lot of psychological effects are in this area. So you can see how much mass this distribution places on these values. We'll use for now this Cauchy distribution, the prior with 0.707 as a scale. And so what's nice about Bayesian analysis is because you place priors on all parameters, you can actually get predictions from the models before ever looking at data. So you can get predictions from the null hypothesis and from the alternative hypothesis like we do here. And so these values on the x-axis are predicted sample effect sizes, predicted observed effect sizes, and there's a density distribution put on them. And so this is really nice because we know how well the null hypothesis predicts a value of 0 versus the alternative hypothesis. And everything we have to do now after seeing the data is compute the sample effect size, plot it in here, and see how well the alternative hypothesis predicted it versus the null hypothesis. So let's just do that. Here's our observed effect size of -0.149. And we can see that the null hypothesis was much better at predicting this value than the alternative hypothesis. And then we can use the Bayes factor to quantify how much better the null hypothesis predicted the alternative. And it's been 3.71 times as good at predicting the data than the alternative. So this is our Bayes factor here. That's our result from this analysis. And just yeah, to show you how to do this analysis in JASP. Let me just open JASP and hope that this works. So here's the JASP interface. If you haven't downloaded and installed it yet, I hope you'll do after the webinar. Let me just show you around JASP a little bit. So here up there are the different options of analyses that you can do. It looks, yeah. And they are grayed out, and the reason is because we haven't any data loaded. So let's do that first. And the nice thing about this example that I showed you is that the data is actually in the data library in JASP. So to open data, I go to open. There, I could either look at data at my computer or recent files anywhere on the computer. You could even go to OSF and look at projects there and get data directly from there. But there's also a data library in JASP that has a lot of example data sets that you can use to try out all the functionalities. And so I'll go to t-tests here, and our example is the kitchen rolls example, and I'll just open the data set here. And as you can see, it opens immediately a data set. Here are all the participants. There are several different variables, and the ones I'm interested in are a little bit further back in the data set. So here's the average openness score, which is going to be interesting and important for us. And as you can see, there's also different types of variables that you can look at. So ours here is a scale variable. There are also ordinal and nominal scale variables. And then the condition we looked at is in the variable condition rotation. So there's clockwise and counterclockwise in here. I can now, as you see, because I loaded data, I can look at all of these different analyses options. Here's the t-test, and now let's perform a Bayesian independent samples t-test together. Let me open this here. It opens an analysis interface, and we can plug in the variables that we need. The mean neo is the dependent variable, and rotation is the grouping variable. And it automatically gives you the Bayes factor. Look here, that's giving you a Bayes factor of 0.27, which is different than what we had before. And the reason is that by default, JASP gives you a Bayes factor in favor of the alternative over the null. And we looked at the Bayes factor of the null over the alternative. So I can flip this here, and we get to our Bayes factor of 3.71. You can also get some plots back from the Bayesian independent samples t-test. For example, we can get a prior and posterior plot here, which shows here the pizza plot that we looked at before. And it shows the prior distribution. This here is the Cauchy distribution with a scale of 0.707, and then the posterior distribution after seeing the data, and also a comparison at null here. So this is pretty useful. You can also get a Bayes factor robustness check, which checks how robust the Bayes factor is against the setting of the Cauchy scale. It loads, it takes a little while to load, but here it is. So it'll give you the Bayes factor in favor of the null over the alternative at several different Cauchy prior settings. Here's the setting we used, and this here is, for example, a Cauchy with a scale of 1, and the Bayes factor changes, and it's actually getting a little, you're getting a little more evidence for the null hypothesis. You could also change the prior in the settings in JASP. So right now we have this scale of 0.707. I could change that to other values, but I could also change it to a normal distribution or a t-distribution. And then another thing that I find very important in t-tests is you don't have to use the alternative that is two-sided. We could also do a one-sided t-test and say, well, our prediction was that rotation clockwise should increase the neo, which means we are predicting that group 1 is greater than group 2. And if I click that hypothesis, I even get more evidence in favor of the null hypothesis over the alternative, because my alternative prediction is more constrained. Okay, so this is all I wanted to show you in JASP and with the Bayesian t-test for now. Sorry, guys. Yeah, let me just scroll to the end here. And here are a few references for the Bayesian t-test, JASP and Bayesian Inference. And with that, I'll give over to Johnny, who will show you a little bit more how to do some practical things in JASP and give a little bit additional examples of doing Bayesian analysis in JASP.
Yeah, hello everyone. Let's see how this all works. So yeah, now that the Bayesian philosophy has been kind of introduced by Alex and a practical example has been given by Julia with Bayes factors, I just want to take this opportunity to first show you one more example in the form of an ANOVA, because it's very commonly used analysis and kind of a tricky thing to do or to interpret in the Bayesian way. And then I want to close off with like maybe some more details about JASP itself as a software. But so first off, let's get back to JASP. So I want to go to the data library again and go for an ANOVA example in this case. And so one example that we have here is called singers. And this is a data set where they wanted to investigate if there was a difference in height between singers, depending on different groups of their vocal range. It's a little silly, but you know, for these types of workshops and especially statistical workshops, you need kind of silly examples to kind of balance things out a bit. So yeah, here we have our data set, and now we want to go to ANOVA. We can select a Bayesian ANOVA. And so the layout is pretty similar to the t-test. We have our input field in the upper left, where we can select our dependent variable, which in this case is height, and put it in the dependent variable box. And then we can add some factors to see if there are height differences between these different groups. So maybe we can try voice and pitch. Select those two and drag them to the fixed factors box. And then immediately you can see on the right, we have some sort of table being outputted here. Let's put this somewhere else. And this is maybe a more classical, like ANOVA type table that you might be used to seeing. But instead of having F values for each effect, we have Bayes factors. And this is really getting back to the main philosophy of Bayesian model selection, because this table gives a model comparison between all sorts of different models. In this column called models, you see all the possible models that you could make with the factors that you added in this fixed factors box. So we see the model here with only the main effect of voice. There's the model with the two main effects plus the interaction effect between voice and pitch. Then the one with two main effects, the one with one main effect of pitch, and we have the null model. And so the null model is the model without any predictors in there. The null model just postulates that all heights across all groups of singers is equal. So this might seem a little bit like a jungle at first, like this table. But I'll just walk you through this step by step, because what the Bayesian ANOVA does in JASP is comparing the predictive performance of all those different models, just like we were doing before with the t-test. But in this case, we don't have two models to compare, the null and the alternative. But in this case, we have all these different models to compare. All these different models make different predictions about the data. And the Bayes factor is a reflection of how well they actually manage to predict that data. But first off, we have the first column, which is the prior model probability. Well, in this case, and this is just done by default. We're working on maybe expand or adding this option, but we just select uniform prior model probabilities. So this means that before we see any data, we just say that all the models are equally plausible. So we just spread out our prior plausibility across all the different models. Then in the column next to it, we have the posterior model probabilities. So these are the model probabilities after seeing the data. So this actually takes the data into account, hence the conditioning on the data symbol here. But the two columns I like the best are the base factor BFM, we'll get back to that in a minute, and BF10. And I want to focus on this column first, because that's a little bit easier to grasp now. And so this BF10, it's comparing one model to another. And in this case, we're comparing each model to the best performing model. There's an option here where you can select to compare either to the best performing model or to compare to the null model. But for now, let's just compare to the best model. The model with only voice part as the main effect has apparently performed the best because it's at the top of the table. And this also explains why the BF10 in this case is 1, because we're comparing the predictive performance of the model with the main effect of voice to the model with the main effect of voice. So they perform equally well, hence the base factor of 1. Well, then if we look at the second line, we get a base factor of 0.8, which means that the full model, so with the two main effects and the interaction effect, that the data are 0.8 times more likely to occur under that model than under the model with only the main effect of voice. So it's slightly underperforming, but there's not a huge difference. Maybe you can think back of the balloons. And so if you would, get your balloons and your pie chart, it would almost be 50-50. For interpretation's sake, I will actually switch now to BF01 instead. So then this 0.8 becomes 1.2. So this means that the model with only the main effect of voice performs 1.2 times better, you can say. Well, this holds for all the other base factors as well. When we get to the model with only the main effect of pitch, we can see that the best model greatly outperforms that. The data are, I can't even pronounce this number. It's a lot of zeros, 34 zeros to be exact. So that's a lot of balloons, right? And it's even better, and the null model is performing even worse. So that's this column, this BF01, and this comparing one model to another. And with base factors, it's always super important to keep in mind what you're comparing to what, because base factors are a relative metric. So it could be that if one model outperforms the other, it could be because one model performs the data very well, but it could also be that the other model just performs very badly. So really keep this in mind, this relative nature of the base factor, because there's no absolutes here, without getting too much into philosophy here. Anyway, so we were comparing two models before, but now if we look at the column BFM, we can compare one model to all the other models. So we have, so we kind of average across the predictive validity of all the other models, and we compare it to a single model. And that's what this BFM shows. So for instance, this BFM of 3 for the model with only the main effect of voice is 3. So you could say that the data are 3 times as more likely to have occurred under that model than under all the other models averaged across. So these two columns, they're both base factors, but they compare different things. And so sometimes you want to look at one column, sometimes you want to look at the other, sometimes at both. It just kind of depends on your research question also. And so this is really model comparison. But so sometimes you also want to just look at the effects. And in Bayesian ANOVAs, this is really easy, especially with JASP. You can just tick this box, effects, and then you get a new table where instead of per model, you get base factors per effect. And the way it works is as follows. So for instance, for the effect for the first line of voice, we look at all the models that include voice and compare them to all the models that do not include voice. So this is again comparing two groups of models. So not two single models, but groups of models. And then we just look at which of the groups of models performs best. So we have some prior inclusion probability. You can this is kind of the same as the prior model probability in the model table. Then we have posterior inclusion probabilities. But then the column I like the best is the exclusion. But if we flip it around, it's inclusion. So this is the inclusion base factor. And that's what you use when you want to compare different effects. Well, we can already see here that the inclusion base factor for voice is infinite. So that's definitely a lot of balloons. Well, yeah, let's maybe look at you know, the interaction base factor, inclusion base factor. So that's about 2. So this means that the data are about 2 times more likely to occur under models that include the interaction effect compared to the models that do not include this interaction effect. Actually, in the case of the interaction effect, there's only one model that includes the interaction effect, and that's a full model. So we're comparing just the full model to all the other models. And maybe if you were paying attention, you might have noticed that we already did this comparison in the model comparison table. Because if you look at the column BFM, that's also comparing a single model to all the other models, right? And so if we look at the BFM of the full model, it's also 2.15. So that's exactly the same number as we see here in the inclusion base factor, because we're performing exactly the same comparison, namely the full model against all the other models combined. So these numbers, you know, they're not pulled from thin air. There's actually some coherence here. And it's a nice thought exercise in keeping track of what you're comparing to what, because that's what base factors are all about. So this is the core of the ANOVA, and of course we're all very time pressed, so we can't go into every little detail. There's a very nice paper that my colleague Don van den Berg just wrote, which is a tutorial to Bayesian ANOVA, so I'll put this on the OSF as well, because yeah, it can cover a lot more than I could do in this half hour. Just want to point you to one new feature that we have, which is single model inference. And here you can get, because this is a little bit more focused on estimation, because so far I've only been talking about testing and model comparison. But if you want to do estimation of model effects, you can get some posterior distributions by selecting this option here. I will. So you get all sorts of different posterior distributions. And you can see that the posterior distributions for pitch are they're all overlapping, which is already also illustrative that there's not a lot of height differences for the different pitch groups. Okay, so that's the ANOVA. Now I want to just, oh my, I can drag this too. Okay, whoa. Now I want to show some more, just some more JASP features. Like one thing I really like when I've done an analysis and I want to share it with students or workshop participants or colleagues, is you can annotate this JASP output. So you can click on these titles and it will usually have a drop-down menu. And you can click to add notes. And then you can write something like, here we did a Bayesian ANOVA, something like that. And in this way you can, did my video freeze?
No, you're okay.
Oh, on my screen it's frozen.
It's only on yours.
So in this way, you can write a full report of your analyses. You can help the reader interpret it, and it just like increases the transparency of your research. Then you can choose to save it, and either upload it to the OSF or save it to your computer. If you choose to upload it to the OSF, let's see if I can Singer's demo. I'm just going to save it now to, let's say, in the datasets folder. And so now I'm uploading my JASP file to the OSF. And a JASP file is basically a glorified zip file. It's a combination of all sorts of different pieces of information. So the JASP file contains the raw data. You can also choose to export it without the raw data if it's like sensitive data, for instance. The JASP file contains the output, so all the tables and graphs that you made, and all the notes. Then if someone downloads that JASP file and loads it into JASP, they can see exactly what settings you used to come to those tables. So it also increases the transparency of how you did your analyses. Then if you go to, can you still see my screen? Mm-hmm. Yeah. So now if we go to the OSF again, and I think it was under datasets. Well, here we see the JASP file that I just uploaded. And the nice thing is that you can just display that JASP file in your browser. So here we see, well, we don't have the input panel, but we have the output, which is annotated. We have our beautiful tables, and you can just access this just as any website. So you can just pull out your phone, pull up your awesome new results, and just show them when you're having coffee with a colleague, for instance. Right. So that's the OSF. Then there's a couple more things, some more resources that I would like to point you towards. We have a folder here with articles, and these are some nice introductory readings for if you want to find out more about Bayesian inference. There's a nice collection of papers written by Alex, as well as some more awesome Harry Potter examples. There is an article that outlines guidelines for how to conduct and also report Bayesian analyses in your research. And then we have our website that you might have visited to download it. And here you can find a couple of nice things, such as the how to use JASP page. And this is a collection, or these are tables with all the analyses, and then indicating if we wrote a blog post or a video or made a GIF file to illustrate how to do these analyses. So first we have the frequentist analyses, and then the Bayesian analyses. It's long from being completed, unfortunately, but yeah, it's a nice start. And then lastly, we also teach some workshops in the summer, at the end of August. And these are a little bit more elaborate because there's only so much you can do in an hour and a half. Yeah, feel free to browse these. So we have a 2-day JASP workshop. So that's a lot more concrete than what we've done today. And there's also a week-long, more programming heavy workshop in Bayesian Inference that goes much beyond JASP. It's in a programming language called JAGS, and this gives you a lot of flexibility for all sorts of funky cognitive models that you might want to do inference on. But yeah, I'll just let you find that out for yourself. Is there anything I forgot or?
Modules.
Modules, yeah. Is my video still on? Because I don't see.
You're on.
Okay. Yeah, so lastly, we also have some modules. Besides these core analyses, you can click on this little plus icon. And we already have a couple of modules. We're working very hard on expanding our collection of modules, and we're also going to make it easier to develop your own module for JASP. But for now, we have a couple of existing ones. We have the network module for doing network analyses, which is a really fast-growing, gaining more and more popularity by the day method of analyzing psychological data. We don't have the time to go into the details. We have a meta-analysis module, which if you just click it, it will just appear in your ribbon bar. You can also unclick it and then it disappears. We have a structural equation modeling module. And one that I really like is a summary statistics module. And maybe I have maybe 2 minutes to demonstrate this.
Mm-hmm.
So this summary statistics module allows you to do Bayesian reanalyses based on just a couple of numbers. So let's say, let's go for a correlation. So you click it, and then again, you get this analysis window.
These out of the way.
Oh, you can see those.
Yeah.
Oh, why? That seems.
I don't know. That's good.
Yeah, so all you do here is input the sample size. So let's say we encountered a research article that had reported a sample size of 30 and a Pearson's correlation of 0.3. Maybe let's make it 0.35. Well, maybe let's make it 4. You know, and as you can see, just based on these two numbers, you can do a Bayesian reanalysis of that result. Well, here we have the outputted table, which reports the sample size correlation, the base factor, and the p-value. You know, so you might have seen such a result where they say, oh, p is below 0.05, so, you know, we won the game of academics. But then if you do this Bayesian reanalysis, you can see that the corresponding base factor is just a meager 2.2, which is really just anecdotal evidence. Yeah, like very little balloons. Yeah, you can get, again, like some prior posterior plots to make it a little bit more visual, which I'm always a fan of. Same as for the t-test and the ANOVAs, you can also tweak the prior settings. So you can make it very wide, or you can make the prior a lot more narrow. If you have some, you know, prior beliefs that the correlation coefficient is going to be closer to 0. Like by default, it's equal to 1, which induces a uniform prior distribution, which just says that all values of the correlation are equally likely a priori. Okay, I think that was my little summary statistics propaganda talk. It's a little weird that we don't have any interaction with the audience.
I'm not sure.
So I hope people are fairly satisfied with what we've done so far. Maybe we'll hang around for a little bit longer in the chat window or in the Q&A to answer some more questions that you might have based on the stuff that we've been talking about. Yeah, anything to add? This was like a really cool experiment. This is the first time that, and I think any of us have done such a webinar. It's kind of weird talking at my computer. I hope there's people listening.
Yeah.
If you have any questions, you can look us up, send us an email. Some of us have Twitter. There's the JASP forum, the JASP GitHub, if you encounter issues, because being up-and-coming software does come with some bugs that might go undetected. So we're also always happy if you report some bugs.